Welcome back. In this lecture, we'll talk about an experiment of the first-order RC filter. So this is the RC filter we have discussed in the previous lectures. Now we are going to test it on the bench. The input source is a function generator with 50 ohm internal output impedance. The output of the function generator is connected to a 0.1 microfarad ceramic capacitor. Now we just built the basic RC filter as we have discussed in the previous lectures. This slide is a quick overview of the body plot of the input to output transfer function. As you can see on the body plot, as the frequency is around 31.83 kHz, which is defined as the cutoff frequency at 0, the magnitude began to decrease at -20 dB per decade. In this experiment, we will focus on the magnitude over the frequency range from 100 Hz all the way up to 15 MHz. This circuit shows the basic setup of the RC filter. On the right-hand side, we have the through-hole capacitor 0.1 microfarad ceramic as shown in the picture. So we have the leads from function generator red and black connected to the at two ends of the capacitor. The function generator, we are using HP 33120A 15 MHz function generator. Again, the output impedance is standard 50 ohm. The output is set as a sinusoidal waveform with 10 volt peak-to-peak voltage. The frequency is ranging from 100 Hz all the way up to 15 MHz during the experiment. This is the basic information for this ceramic capacitor. We are using 0.1 microfarad 50 volt rating X7R radio capacitor. We measure the output voltage using the passive probe at the oscilloscope. Remember, we only have one voltage measurement in the experiment. Since the setting from the function generator is set at 10 volt peak-to-peak, we only measure the output voltage. At 100 Hz, this is the waveform at channel 1. On the right-hand side of the scope capture, we have the measured frequency around 100 Hz, and the peak-to-peak voltage is 10.3 volt on the oscilloscope. The function generator is set as 10 volt peak-to-peak. The difference between the measurement and 10 volt settings is coming from the measurement noise on the traces. At 1 kHz, the peak-to-peak voltage is still around 10 volt. At 10 kHz, you can see the magnitude began to decrease. At 100 kHz, the output magnitude is significantly reduced, since the frequency now is above F0, which is 31 kHz. Now we further increase the input frequency. At 1 MHz, the peak-to-peak measurement is only 256 mV. At 2.1 MHz, the peak-to-peak voltage across capacitor is further reduced as 140 mV. The results so far are as good as we expected. Now the frequency at 5 MHz, but all of a sudden we can notice that the output magnitude began to increase. The question is why? If we zoom in and look at 10 MHz, the peak-to-peak voltage is further increased as 784 mV. If we increase the frequency up to 15 MHz, we notice that peak-to-peak magnitude is over 1 volt. We know that inductor impedance increases at higher frequency. Now, the capacitor behaves as an inductor. The question to you is, can you explain this behavior? We notice that as frequency goes up above 2.1 MHz, the output voltage peak-to-peak increases as well. The question is, what's wrong with the RC filter model, where the capacitor behaves like an inductor? So this is the schematic we are using in the previous slides. So what is wrong with this model? Apparently, this capacitor model is not ideal, so we can expect to see some parasitics. The parasitics comes from the external leads and the internal structure. We need a realistic capacitor model to explain the capacitor impedance over the frequency range. On the right-hand side, this is a realistic model for a capacitor with ESR, which is the name for parasitic resistance, and ESL, that is the parasitic inductance. So we have two more elements in series with the ideal capacitor C. In the picture, you can see I intentionally increased the length of the leads into the circuit so that we can notice this problem more easily. In a new experiment, in order to reduce the parasitic impedance, we can minimize the lengthy leads by putting function generator connectors right next to the capacitor. In this case, the function generator clips are put as close as possible to the capacitor so that we can minimize the ESR and ESL from leads. Now we understand the importance of the capacitor model over the entire frequency range. Also, I show you that capacitor leads can add ESL that increases the capacitor impedance at higher frequency. Recap: in this first-order RC filter experiment on bench, I show you that capacitor model is good under low frequency, for example below 2 MHz, but it is no longer true at higher frequency. At higher frequency, the capacitor may behave as an inductor, which is definitely not what we want. For higher frequency design, we have to choose a capacitor carefully so that it works as a good capacitor, not an inductor. It is a good practice to minimize the parasitic inductance as much as we can. For example, for through-hole capacitors, we can minimize and clip off actual capacitor leads. On the PCB, we should use short and wide traces to connect capacitors. Thank you and see you next time.